Okay, let's get started here. So today we're going to talk about speculative parallelism and computer chess. But first, let's just talk about the home stretch. So we have just a few weeks left of the semester, and it has certainly been an unusual semester by any measure. I am rooting, and as are the entire 6172 course staff, for everyone to make a strong showing at the end. And I think it'll be helpful if we take a minute and look at what the home stretch will look like so that you can plan your time wisely. So today is our last regular lecture. And then on Thursday, as you know, we have quiz 2. And then Friday, we'll offer help with project 4. And then everyone goes home for Thanksgiving for a week. Well, actually, about 25% of you, I guess, because the rest of you are already home. But in any case, everybody's leaving MIT who's still at MIT. Please do not overwork on project 4 during the Thanksgiving break. We size the project so that everyone can do well working just regular hours without overtime. Not that any of you listen to me anyway, but that is what we try to do. So while you're home, I'd like to send you a remembrance of 6172 and this unusual semester. Okay, so can anybody tell me what this is?
Is that a bit mask?
It is a bit mask. Well done. It's a MIT 6172 bit mask. Okay. And I plan to mail a bit mask to everyone in the class. And my plan is to use your home address, which I got from WebSys, unless you want me to mail it elsewhere. So we'll put up a Piazza post, which will provide details on how you can change the mailing address. Okay. But I thought, you know, what better thing to celebrate than a 6172 bit mask. Okay, back to the home stretch. So hopefully sometime during the Thanksgiving break or shortly thereafter, you will get your bit masks. But after that, we have 2 guest lectures, which I'll tell you more about in a moment. And then finally, a final wrap up with your recitation instructors. So please remember in that final session to thank them for all the effort they've put in this semester to help you do well in the class. They have been amazing during this really, really difficult time, and they have been uniformly dedicated, okay? Then your project 4 oral presentations will be scheduled across the day on Tuesday, December 8th, and we'll try to do the scheduling this week. Okay, classes end on Wednesday, December 9th, and we'll have the Lyser Chess exhibition tournament on Thursday, December 10th at regular class time, 2:30, but there are no classes that day. So I hope you can tune in and watch your bots compete, okay? So in just about 3 more weeks of class, we're all done. Good. Now, the first of our final guest lectures will be by John Bentley of Bentley Rules Frame. John is definitely a grand old man of performance engineering. Don Knuth is probably the oldest student of the field, but John's contributions were early and seminal. He was also a pioneer in computational geometry. And if you can believe it or not, when I was an undergraduate, the idea that geometric data had interesting algorithms was brand new. John made many significant contributions to the area, including inventing KD trees, which is a data structure used for multidimensional range searching. He also happened to invent the master method for solving recurrence. Anyone ever hear of that? And he wrote several impressive books. His Writing Efficient Programs was the one that introduced what we now call the Bentley rules. He also wrote a regular column in the Communications of the ACM, which is the flagship magazine of the largest organization of computer science professionals in the world. And let me recommend that you join while you're a student. He compiled those essays into 2 books, Programming Pearls, and really quite originally, I thought, More Programming Pearls, which are both highly entertaining and instructive even to this day. He's won many awards, including the industrial Dr. Dobbs Award, because his impact has been felt far beyond the halls of academia. So you won't want to miss, this is my sales pitch, you won't want to miss this chance to meet and learn from a real computer science celebrity, okay? And I should mention that he's had some well-known academic progeny, okay? So you'll remember the lectures by Tim Kaler, which was last time, and Bruce Maggs on networks, and Angelina Lee on the Silk runtime, and T.B. Shardle on compilers. Well, John was the academic grandparent to them all. Okay, every one of their PhD thesis advisors had John for a PhD thesis advisor. Okay, and I'll leave you as the puzzle as to who their advisors were. Okay, and you can share that on Slack. Okay, but let's move on. Okay, to the content. So our second guest lecturer is a mystery guest. Okay, he is a brilliant engineer who is a leader in GPU software technology. He's had a huge impact on industry, a fabulous sense of humor. He's won awards. He's a prolific writer, and at least one of the above is true. Okay, actually, they're all true. Okay, so don't miss it, and we'll reveal later who this guest lecturer is. And I think you will. This is not a lecture you'll want to meet. You'll want to be there for both. So John Bentley on the Tuesday after break and the mystery guest on the Thursday. Great. Okay, let's get to the topic. Okay, this is about speculative parallelism. Now, speculative parallelism is a particular type of non-deterministic parallel programming, which means that you shouldn't ever do it. Okay? Except when you have to. And why might you have to? Good quiz question. So on Slack, why might you need to do it? Yeah, performance. Yep, you got it. Okay, you need the performance. That's why you do anything crazy, right? It's like, we need the performance. Okay. Yeah, when you want an A in the class. I like that, Sheng Tong. Very creative. So speculative parallelism occurs when you guess that it's probably worthwhile to compute something, but you might be wrong. And if you're right, you get to do the work in parallel, making the code run faster. But if you're wrong, you waste resources. So let's look at a simple example. So here is a function find that takes an array S of n integers and a key, and it's simply going to check whether the key is in the set. Very simple program. Okay, if so, it returns true. If not, it returns false. But this code could be more efficient than it is. So basically what it does is it sets found to false. It runs through. As soon as it finds something that's true, it sets found to true. And then when it's all done, if found was set to true, then it will return true. And if found was never changed, it returns false. Okay. But as I'm sure you can all tell, this code could be much more efficient. Okay. Because once you find an element, you can stop searching. Okay. Whereas this just keeps going, even though it knows what the answer is. But notice that this code would be pretty easy to parallelize. Okay, if I did a Silk 4 there, it would basically work. You have a little bit of a benign race But there are other ways of dealing with the benign race, or you could leave it as a benign race. Okay, so let's look at a more efficient version of this. Okay, so here we go once again as we're running through it, but this time, as soon as we see the key, we return true, okay, and otherwise return false, okay. Much better code. But how can we parallelize it? Because Silk does not let you execute a return out of a Silk for loop, okay. So you're in a little bit of trouble just doing a Silk for. But although Silk won't let us do what we want easily, we know that Silk implements parallel loops using divide and conquer. So we can use divide and conquer to exit the search earlier. So this is a function. Here's a pfind, okay? And what it does is it sets a variable to false, and then it calls this find helper, passing the address of found as an argument. And find helper is at the top here, okay? As it executes, it first just checks, has it found it? Okay, if so, it returns, okay? And then when we get down to n equals one, and of course you probably want to coarsen that, and you, if it's got the key, then you return true, okay? So that's the base case, okay? Otherwise, what it does is it divides the set of keys into two subsets, okay, each of half the size. It calls one, and then it checks found, okay, before syncing, okay? So if it happens to execute serially, okay, we execute one, then the other, and it happened to find it in the first set, we never bother calling the second pfind helper here, okay? But if not, then it calls the second one. But of course, every one of them, whenever it starts up, it's checking found. Okay, so it finds out and returns, pretty early. And although, this is kind of lightweight work, you're not really doing much work. So it's not clear how much this helps compared to how much extra stuff you're doing in the loop. It's arguably you could do this. Okay, and if it were a much more expensive operation, it might even be worthwhile. Okay, now let's make some observations here. So first of all, the obvious thing, this code is non-deterministic. Okay, so skull and crossbones, it may behave differently on each run of the program. You're going to have to cope with that. Okay, second, okay, if the key occurs more than once in the set, okay, technically, then we're searching a multi-set. We could have a race on found, okay? It's a benign race, although you have to recognize that some people don't believe there is such a thing. And the reason is because it is dangerous, okay? Some computers do not support atomic writes to bite-sized variables such as bools, okay? The C standard doesn't actually say it, but GCC, LLVM, and other compilers treat ints as atomic, which should be safe, at least for a while. So if we declared, instead of having a bool found, we had an int found, it probably works on most architectures, okay? And then we're changing something at the same time. So do I need a memory fence here? Okay, so do people want to respond in Slack? Do I need a memory fence? No question mark. No, since they all set to the same value. No, you're only setting it to true. All those are kind of right. We can't guarantee that the write to found will eventually be visible to other threads in a reasonable amount of time, but that doesn't actually affect correctness, okay? So in the right to found may be delayed, but it doesn't really matter because the value is monotonic. It transitions from false to true and never back to false. So in the parallel loop, if found becomes true and a processor doesn't notice for a while, okay, so it keeps executing. Okay, you're doing extra work, but it doesn't affect correctness. Okay, so you actually don't need a fence there for this code to, it's correct without a fence. Okay, and in fact, the fence may cost you more than just simply waiting what you might waste if you don't do it. And these are things that can be very system dependent. Okay. Now, it can be annoying when you run silk sand to get false positive warnings due to the benign race. And so this is one of these cases where you want to use silk's functions, silk sand disable checking and silk sand enable checking to suppress the race. So I'm not sure you want to, but that's one option. And the reason you might not want to do is, like anything with non-determinism, it can be dangerous because you may have a real race bug somewhere that you're inadvertently suppressing. Okay, so you think you're only disabling in the right place, but in fact, there's another race, and now you've told silk sand not to worry about this other race. Another strategy, which is probably safer, is to provide your own C preprocessor option to allow you to selectively disable this non-determinism. Okay. And so generally, when you have different sources of non-determinism, I recommend that you use a different option for each of those. Okay. So rather than having a single program-wide flag, well, actually, it's helpful to have a single program-wide flag that sets them all. But when you've got a problem, it's helpful to be able to narrow down the cause quickly. And so if you can control them individually, you can say, does my bug occur when I turn them all off? Does my bug occur when I only have this one on? What about only this one, et cetera? And you can go through and it becomes quicker to debug. Okay, so this code was an example of speculative parallelism. The speculative parallelism occurs when a program spawns some parallel work that would not be performed by the serial projection of the code. Okay, that's pretty much the definition. So here's a good rule of thumb. Okay, don't use speculative parallelism. Okay, unless there's no real opportunity to obtain parallelism elsewhere. Okay. And don't do it unless there's a good chance it's needed. Otherwise, you may find yourself simply wasting work. Okay, you may look and, wow, you got a good parallel speed up on P processors, but you're also doing P times as much work. So your net speed up, okay, is over the original serial code is 1, or sometimes with overhead can even be less. Okay, so that's basically speculative parallelism in a nutshell. We're going to apply it in a more complicated setting, but I wanted to give you a simple setting to begin with. So any questions on Slack? Or if people want to pipe up? See, it looks like here is typing. That's always a good way to get somebody to stop. Okay, I'm going to move on. Oh, no, here we go. How does the analysis of speculative parallel code differ if it's doing work different from the serial projection? Well, what you have to do is you have to say, it's going to generate its own, trace, its own execution DAG, okay? And you will get, the Silk scheduler will give you speed up according to whatever that DAG is that's produced, but it's a non-deterministic DAG. And so, how much more work you're doing, well, that's, sometimes you have to analyze and sometimes you can't analyze. You can just say, well, empirically, it seems to be small. Okay, and that's kind of the situation we're going to be in as we look at our next topic, which is alpha beta search. We want to parallelize alpha beta search. And as far as we know, speculative parallelism is essential for searching game trees in parallel. Okay. So is this topic relevant to anyone in the class? Parallel game tree search? Okay. Maybe. If so, okay, you'll want to pay attention. Okay. So first, what I'm going to do is just review alpha beta. Okay. So you saw it last time, but I want to go through it again so that we can see what the difference is. So here's the code for alpha beta, a code for alpha beta. We're searching a position X in a game tree using an alpha beta window. And we have a depth D that we're searching to. Now, if D equals 0, we've reached the end of our search, okay? But we may also end the search because the game is over. It's what they call a terminal position, like a mate in chess or a king being zapped in Lyser chess. So if we have essentially a terminal position, we compute the static evaluation of the position and return it. There's nothing more to be done here, okay? Otherwise, we get into the interesting part, which is we generate all the positions that can be reached from X, and then we go through each of the children and search them recursively with one less depth. Okay, so, and what I've given here is the so-called negamax formulation of alpha beta, and I'll switch between these, between the negamax and the minimax. So in the negamax, instead of having two search routines, one doing maximum and the other doing minimum, we negate all the values in switching between the two so that both sides can do the maximum. Okay, the min guy just does the maximum on negative values. Okay, that's all there is to it. Okay, so it just simplifies the code a little bit. Okay, now to help visualize the last few lines of code here, okay, after I've generated the moves and I now have done the search, let's look at a graphical representation of the space of search scores, okay, which stretches from -infinity to +infinity. And on input, we're given an alpha beta window, okay, which could be -infinity and +infinity. So alpha is the best outcome we've been able to achieve so far. And beta is the value which, if we exceed it, the other side won't select the move on the previous turn that led to this position X. Okay, so back to our code. We've just searched the first child, okay, yielding a value of S. Okay, and let's say that S falls below alpha, as I've indicated with the red dot here. Okay, in that case, if you look at the two if statements that are these two guys here, okay, neither of them execute, okay, and so we ignore the value and we just simply move on to the next child. We search again, okay, because we haven't figured out something that's actually better than our current alpha, which is the best thing we've seen so far. Okay. Now, this time the dot falls between alpha and beta, as indicated by the blue dot. Okay. In this case, the first if statement says, okay, this one here says that we update alpha. Okay. So that's what we do. Okay. So we update alpha. Okay. The alpha beta window got smaller because we have a new lower bound on the best score. Okay. And on to the third child. Okay, here, once again, nothing to do but keep searching. Okay, here's another one that falls within the window. So we update. Okay. Notice, by the way, that if we had searched the blue dot, the second blue dot first, the order here makes a difference that we search the children here. Because if we'd searched the blue dot, the second blue dot first, okay, this guy here, okay, then this one would have fallen outside the window and we wouldn't have done anything, okay? It would have just passed through, okay? And now here we have a value better than beta, okay? And this is like we celebrate these. Hooray, we update alpha, okay, to be up to the new value, and the alpha beta window disappears because alpha is now bigger than beta. Okay, this is the situation that's a beta cutoff. We have a move so good that the other player would never play the move that leads to this position because the other player can do better than this. So we can return, and we don't need to search any more children. There may be 50 more children here to search, but we don't have to look at any of them. Okay. Now, suppose that we had a best ordered tree where the first child was always the best among its siblings. Okay, so let's just think about this. Suppose we had a best ordered tree. The first child is always the best. Then we only would have had to search one child, okay, the best one, okay, in this case, if it were above the window, and the others would have been pruned, okay? Now, if the best one happened to be below beta, then we have to look at all of them, okay? But if it's above beta, then we don't have to look at any of the others. So you can see why so much effort goes into heuristics for move ordering. Okay, let me take some questions here. Okay, this is all just background on alpha beta from last time. And some of you may have seen this in classes like 6034 or something like that. Okay. Any questions here? Okay, kind of background. Just make sure that everybody understands it because it's going to get complicated. Okay, good. Okay, let's see how alpha beta affects the work involved in a search. So we want to try to analyze this. Now, since game trees are complicated and they're non-uniform and they're hard to analyze, most theory in this area considers trees with a uniform branching factor and a uniform depth, and that gives a lot of intuition for what's going on. So here's a game tree. It's got branching factor, in this case, 3. Okay, the tangerine squares represent the maximizing player, and the lavender circles represent the minimizer. Okay, so now let's consider a uniform game tree with branching factor B and depth D. And let's count up the total number of nodes, which is proportional to the work that a naive brute first algorithm, no alpha beta, would execute, assuming that the static evaluation can be done in constant time. Okay, so here we have one node at the root here. Then we have B nodes at the next level, B squared nodes at the next level, and so forth until we get B to the D nodes at depth D. Okay, well, that turns out to be pretty close to B to the D because the sum is geometric and the leaves dominate. Okay, so it's really just approximately 1 plus 1 over B to the 1 plus 1 over B bigger. Okay, if you take just the first order, and if you take more, then you can get it closer. But you know, B to the D is going to be close enough. Okay, the leaves dominate. Okay, now let's look at alpha beta, and let's consider a best ordered tree. Okay, where the first child at each node always returns the best score among its children, although the algorithm doesn't know that. Now, in 1975, Donald Knuth and Ronald Moore proved a really wonderful theorem about this. They showed that the total number of positions examined at depth K is exactly B to the ceiling of K over 2 plus B to the floor of K over 2 minus 1. So I'm showing the subtree that alpha beta examines with yellow highlighting. Okay, so what gets clipped and so forth. So even in this case, the leaves dominate, giving us about 2 times B to the D over 2 nodes overall. Okay, so that's going to be a close enough approximation for what we're talking about. And even that 2 is kind of annoying sometimes. And sometimes I may just say B to the D over 2. Okay, so that's really a remarkably neat theorem, actually. If you look at how it's not actually very hard, okay? And the paper is in the literature and is really not very hard. It's right near the beginning. They do a lot more complicated things later in the paper that I think nobody reads, but this part they read. Okay, so what does that mean? Okay, how do we compare alpha beta with a naive algorithm, the brute force algorithm, which, as we saw, examines about b to the d nodes? Okay, since alpha beta examines two b to the d over 2 nodes, that means that alpha beta can almost double the search depth before it examines a comparable number of nodes. So it can search twice as deep for the same work. Okay, that factor of 2 is a little annoying, but as I say, we're not too terribly wrong by ignoring it. Now, if I write b to the d over 2 as the square root of b to the d, okay, then we can see that alpha beta effectively square roots the work of the naive algorithm to search to the same depth. Okay, so it basically square roots. If you go to the same depth, it's only searching square root the number of nodes. And then another way we can write it is as the square root of b to the d. Okay, and then we can see that really what it's saying is that we're effectively square rooting the branching factor of the search. It drops from b to square root of b at everything. So those are all equivalent ways of understanding alpha beta on a best ordered tree. Okay, another observation made by Knuth and Moore, as well as by others, is that in a best ordered tree, the degree of every node is either 1 or b. You examine only one child or you examine all the children, okay? So here, the best child has a value above beta on this number line that I've written down, okay? If we search it first, we get a beta cutoff right away and we don't need to search any siblings, okay? So it only has one child. It only searched recursively that one child, okay? Now, in the second case here, the best child has a value less than beta. Okay, in this case, you've got to search all the children, okay, because you're never going to get a cutoff to stop earlier, okay? So you can see why move ordering is important, because we want those beta cutoffs. We're hoping for that first case as opposed to the second case. Well, the second case you're going to get, okay, but you're hoping to get good move ordering, because if you get good move ordering, then if you're lucky enough to be in the first situation, you can just search one child and then you're done, okay? Okay, so the observation that in a best ordered tree, nodes have either maximal degree or a degree of 1 leads to many speculative parallel algorithms for alpha beta search. Okay, so now we get into the real content of the lecture, parallel alpha beta search. Okay, so years ago, a group of researchers at Paderborn University in Germany came up with a great idea which drove the research in this field. Okay, to many people at the time, alpha beta had seemed inherently serial. Okay, if you try to speculate by examining nodes further ahead in the serial order, you might waste a lot of work examining nodes that would have been pruned. Okay, what the Paderborn research group proposed was what they called young siblings weight. Actually, they called it young brothers weight, but these days we call it young siblings weight and relegate young brothers weight to the history bin of unnecessarily sexist language. Okay, so the idea of young siblings weight is to search the first and hopefully best child of a node, okay, first, okay, leaving the remaining children to wait until the search of the first child returns, okay? So then if we're searching it first and the others aren't being searched, okay, in parallel, okay, we just searched the first one, as if it were a serial execution. But if it happens to generate a cutoff, we haven't wasted any work, okay? But if it fails to generate a cutoff, then with a good move ordering, the remaining children should all be worse. So we have to search them all anyway. But now there's little harm in searching them in parallel because there's not going to be much speculation. So you can see how important good move ordering is. Okay, it either helps us get a cutoff or it guarantees us that we can do things in parallel without wasting any work if we had perfect move ordering. Okay, so by looking at a best ordered uniform tree, we can get an idea of the effectiveness of the young siblings weight strategy. Okay, so the work of this algorithm is the same as for ordinary alpha beta search, which is about B to the D. You're still searching the same stuff. Okay, but to analyze the span, okay, since the search of children 2 through B operate in parallel, okay, we only have to wait for the worst of those, okay, right? Because we're taking a maximum. It's as if we only search one of them. And of course, we're searching the first child, not in parallel, and then we can view it as if we're searching one. So the span is equivalent, therefore, to the work of a best ordered tree with branching factor 2, okay, which I've shown here in green, okay, which is we just apply the formula for what happens if I had a best ordered tree with branching factor 2. Well, it's about 2 times 2 to the D over 2 instead of 2 times B to the D over 2. So that's the span, okay, 2 times 2 to the D over 2. And now the parallelism is the work divided by the span, or approximately, therefore, B over 2 to the D over 2, okay, because it was essentially B to the D over 2 for the regular alpha beta. And now we're dividing that by 2 to the D over 2, okay? Now, that's a little bit abstract, okay? And you say, well, is that good or bad? Well, let's get an idea of what that means. So suppose you search 1 billion nodes in a depth 10 search, okay? So and in fact, that's that number is, to get that number, I ran the reference Lyserchess bot to depth 10, and it searched about 1 billion nodes, okay? So the work is therefore about 1 billion, because we searched that many nodes, you know, more or less. I mean, I know there's variability there, but, you know, but the span is now around 2 times 2 to the 10 over 2, which is 2 times 2 to the 5th, which is 2 times 32, which is 64. So the parallelism is therefore about 16 million, which I assure you is not puny, okay? And as you know, whenever you have ample parallelism, you should think about ways of trading some of it for other desirable properties, okay? And here we have ample parallelism, okay? So among the things you may want to do is trade it for the chance that maybe we'll have even less wasted work, okay? Because there's lots of parallelism to be had here. So questions on Slack? Any questions? Are we good here? Okay. Okay. So, but this analysis doesn't account for what can go wrong. Okay, this assumed it was all best ordered. Okay, and then you search exactly the alpha beta tree, but you get to search it faster because, you know, you're able to search the subsequent children in parallel, okay, after the first child. So suppose that the best move is not the first move that we explore from a given position. Okay, then what? Well, we're going to waste some work, okay? But let's take a look at an example and then we can figure out a way to deal with it. Okay, so here's a here's an alpha beta search example. Okay, and I'm going to run through it with just regular alpha beta, and then I will, and then I'll go through and look at it with the young brother's weight concept. Okay, so in the leaves, there are a whole bunch of values representing the static evaluation. And what I did here was I put zeros in places where the value doesn't really matter, so that you can focus on the important values. Okay, so the zeros mean, you know, the value doesn't really matter. And so we're going to search it serially left to right. Okay, and later we'll look at the young sibling's weight and compare. And as it turns out, we're not searching it in best move order. Okay, so the serial algorithm starts at the root, and then it heads down this way until it gets to the first leaf. Okay, and now once you evaluate that, its tangerine parent, which is doing maximization, knows that the value that it's going to have is going to be at least 2. Okay, so then we check the second child. Okay, and the second child is 3. Okay, so this tangerine node's value must be at least 3 because the node maximizes over its children. It's taking the maximum of 2 and 3 up to this point. Okay, and then we check the third one, and it's no better. Okay, we have a 0 in this case, but it could have been any other value less than 3. Okay, and since we're done with all the children, we know that this is actually equal to the value. Okay, not just a bound on it. And so it's now able to return to its lavender parent here, which is a minimizing node. Okay, and so it knows that its value is going to be less than or equal to 3. Okay, so here we're doing regular alpha beta here, not negamax. Okay, I'm just keeping things as alpha beta. Okay, just I'm showing it in terms of constraints. Now, since it's minimizing, okay, when it searches the next child and it gets a value of 7 and discovers this is greater than or equal to 7, it knows that the value is going to be less than or equal to 3. So it's never going to have to bother worrying that, because min is never going to pick this path, okay, and give the max, the tangerine, a chance to go to 7. It's always going to pick this. So we don't have to worry about what these values are. They just don't matter. Okay, so we don't have to search these other 2 leaves. Okay, good. And now we do the same thing for this one. We find the value is 6. That constrains this to be greater than or equal to 6. And once again, because we're looking at, we know that the value is less than or equal to 3, we say, oh, okay, he's never going to pick this one. Why should he go for a value of 6 when he's going to get a value of 3? Okay, and so we're done with it. And so when it looks at all these values, you can see that the value must be 3. Okay, that's going to be the best path. Okay, on to the root. So the root is a maximizer, and since it found a child of value 3, its value must be at least 3. Okay, and now we head down the root's second child, okay, to its first child all the way, okay, which is 6. Okay, and when we search all 3 of these leaves and we're maximizing, we're going to get a value here of 6. Okay, and that's going to therefore propagate up to the lavender node here to provide a bound of less than or equal to 6, because it's minimizing. It knows that it can, you know, if it goes this way, it's going to get 6, but it may be able to do better for the others. Okay, and now tangerine's parent, let's see. So now since, yeah, so he's going to pick this one no matter what. Okay, no matter what the value of the other 2 leaves. Okay, so now it goes and it takes a look at this child and it's got a value of 7, so it's never going to pick that. Okay, and so we can cut those. Okay, and then it goes down to 5. Okay, it gets a value here of 5, but it knows the value is less than or equal to 6. It doesn't know that this isn't better, so it has to evaluate the other 2 leaves. Okay, and it does that, gets a value of 5, and now since this is minimizing, it discovers a value of 5. Okay, so because we didn't look at the best one from first here, okay, we ended up having to completely search this tree. We didn't get any cutoffs. Okay, so now that allows us to propagate this up, and we now know that we have a value of at least 5, because I've got a 5 here and a 3 here, and I'm maximizing. So I know I can get at least 5. I'll take this. I'm not going to take that one. So once again, this node did not pick the best thing that it could. Okay, so now we go down this side, and we find the value of 4 here. Okay, and that's going to be a value. I know that I can get at least 5. Okay, so I can propagate the 4 up here. It's a minimization node, so it's going to have at least 4, at most 4. Okay, and now it's like, oh, well, why should it go for a value that's at most 4? It's just going to take, might as well just take the middle. The root will just as well take that. So there's no point in searching these 2 subtrees over here. Okay, and so that then, when it returns, it's able to set the value of the root to 5, and that's the value of the search tree. Okay, now the second child here, let's look at who caused this great big cutoff here. Okay, that cutoff was from the second sibling. That's this guy over here. Okay, that lavender node provided the cutoff. Its value of 5 allowed us to terminate the search even after the third child of the root could be determined to produce a value of at most 4. Okay, the first child of the root has a value of 3, which would not have caused a cutoff if we had searched them in the order, the first one, then the third one, and then the second one. But because we did it in this order, we got something that was better that allowed us to have the cutoff. It would have been best overall to search this one first, okay, to search the best one first. Okay, so as I say, that's why move ordering is so important. So let's remember that. Okay, now let's look at what happens with young siblings wait strategy. Okay, so the idea here is that with young siblings wait, we're going to march down the side of the tree as before. Okay, and when it comes to search, I'm going to take it up to the point, because it's just more interesting there, of where I'm searching the children of the lavender node. So I've already searched the first child. We didn't search these because these are younger siblings. They have to wait. Okay, first one has priority. Okay, and so now these 2 nodes can be searched in parallel. Okay, that's what the algorithm does. Okay, it looks at both of these nodes and says, hey, I'm going to search them in parallel. Okay, knowing that any value greater than 3, and they know that any value greater than 3 will trigger a cutoff. Okay, which is really great. Okay, and so after searching the first child, this one discovers that it has value at least 7. This one has value at least 6. Those both generate cutoffs. And so now we're back to the first discovering that this has a value of 3, and we propagate that back to the first subtree root. And so we now know that the value is at least 3. Okay, so now we've finished the first subtree. So now we can search these 2 guys over here in parallel. Okay, so we can do parallel recursive searches for those guys. Okay. However, they only know that the root has a value of at least 3. Okay, last time, the second child had that exact information. It knew that the value was at least 3. But the third child here had more information. It knew that it was at least 5, but now we're dispatching before knowing that it's at least 5. Okay. So then when we do the search, we search this guy, we get the value of 6. We now know this has a value of at most 6 because it's minimization. Similarly, in parallel, this guy has a value of at most 4. Okay. So last time, this value of at most 4 was enough to cause a cutoff, okay, because of these guys over here, of these last two little subtrees, okay? But this time, no such luck, okay? Since the search of the second child of the root hasn't finished, okay, this guy hasn't finished, okay, the third child doesn't know that the second child's value is going to be 5 and produce a cutoff constraint of s greater than or equal to 5. It only knows that s must be at least 3. Okay. So then we do parallel recursive searches here, which we wouldn't have had to do, before. Okay. And we're executing now work that the serial algorithm didn't. So we're clearly speculating. Okay. Because we're executing work that the serial algorithm didn't. Okay. And the search, it turns out, of the second child of the root, this search can't help prune the third child's subtree because it doesn't have that information. Okay, so these two guys, the value from the second child of the root is not yet available to prune those searches. Okay, so wasted work is inevitable. Okay, but that's basically the problem, is that what we want to do is try to avoid and keep track so that we don't create much, wasted work. So one of the things that people did in this space was they tried to propagate new information and abort searches when they discovered they were unnecessary. So here's one possible idea that people have tried, okay? And it's not actually a very successful idea, okay, in my opinion, okay? Their idea is that when a node produces a score, propagate the score up the tree immediately, as far as it needs to go to keep alpha and beta current in all ancestors. Okay. For example, when the root's second child, okay, produces the value 5, it updates the constraint in the root from this s greater than or equal to 3 to being s greater than or equal to 5. It writes that. Okay. Now, as the nodes execute, they pull up the tree to get the latest values. Okay. So for example, when the root's third child, okay, produces the constraint s less than or equal to 4, okay, it pulls the root. Okay, so it checks the root. Okay. And it discovers the new constraint. It reads that constraint. And at this point, it can realize that searching its subtrees is useless because the constraints are incompatible. Okay, we basically have a cutoff situation. And it can abort the unnecessary work. Okay, it doesn't have to keep going on that stuff. They can use a trick, with abort flags similar to what I showed you in the speculative computing at the beginning. Okay. So it turns out that this approach is complicated and hard to get right. Okay. And so I don't recommend you use this approach. People have tried it. Okay. It's complicated. You will, tear your hair out unless you're like me and have no hair to tear out. Okay. But, historically, I can say people have not had much luck with this approach. Okay. It's not only hard to implement, it also has dubious efficiency, and it relies on lucky scheduling. And in this example, if the value of the root's second child can make its way to the third child, you win. Okay. So if this can propagate there, you win. But if things happen in the opposite order, which can happen in a parallel setting, then you lose. And you've spent all that time trying to propagate values all over the place. Not a very good strategy. So in practice, parallel alpha beta search always wastes some work. And what your goal is in implementing your particular algorithm is to balance two, actually your goal is to balance two goals, okay? Conflicting goals. One is to avoid unnecessary work. That's the work first principle. The best way to do that is execute serially. But then you violate the second one, generating sufficient parallelism to guarantee a good parallel speedup, that is, have more span. And you don't need oodles of parallelism, just enough to have a parallel slackness of 10 or 20 on the available hardware. Okay, so you want to balance those two goals. Now, here's a parallelism strategy that has worked well in practice. It's called Jamboree search, and it was invented here at MIT by Bradley Kussmaul. Now, I don't want you to think you'll want to implement exactly Jamboree search because it has some complications. But you'll probably want to do something similar in spirit. And we're giving you some guidance to do something that's a little bit easier, okay? So understand the gist of what I'm about to teach and don't worry so much about the details of the code. Okay, so now modern game search algorithm, such as Judea Pearl's Scout search, which is what's in your code in part, use this concept that I'm going to explain of a zero window search. Now, frankly, I never quite understood why they call it zero window because it actually has a width of 1, but no matter, okay? The idea is that when you have a tiny window, it essentially tests whether a score is less than or greater than alpha, okay? And because a zero window is narrower than a full window, you can prune more aggressively. So for example, the full window at the top here shows a situation where alpha and beta are relatively widely separated. Any of the green children here, if you happen to search them, will cause a cutoff if they exist, okay? But if you search and one of the red or one of the blue nodes, you don't get a cutoff, okay? But if you narrow the window, okay, as shown in the zero window one, to where beta is just alpha plus 1, okay, then you may not get exact values for some of these values, okay, but there are no blue nodes, okay? They've all been turned into green nodes, okay? And so you have a better chance of producing cutoffs, okay? And now I want you to notice that if you call alpha beta with a window that's a zero window, then in the code, it's only narrowing that window, okay, or having a cutoff. So it can't get any narrower. And so you end up with a zero window search in all the descendants. And so that's a nice property because it means you're going to prune aggressively on both sides of the equation, both for min and for max. Okay, here's Jamboree search, okay? This was invented, as I say, by Bradley Kussmaul. He actually turns out to be another performance engineer whose PhD research advisor had John Bentley as a PhD advisor, okay? So he combined the ideas of Scout search with young siblings' weight to produce a very effective parallel algorithm called Jamboree search. And here's the pseudocode, and we'll walk through it, but you're going to want to study this on your own because it takes, it does take some things. It's a little bit more daunting, looks more daunting than it is once you become familiar with. It starts out like many game tree search algorithms, okay? It tests at the terminal position, performs a static evaluation, generates the moves, and then it searches the first, which in this case is going to be the 0th move, okay, recursively using a full window search, okay? So it uses minus alpha, it uses alpha and beta, and in the reverse with negamax, you negate those values, swap them and negate them, okay? Now the algorithm keeps its best score in the variable b, okay? And it checks for a beta cutoff and whether alpha should be updated, okay? But now it executes after it's done the first child. So it's doing the first child like young brother's weight. It doesn't do any of the other children, just the first one until it gets back a value in the full window search. And then if there's no beta cutoff, okay, here, then it's going to speculate that this 0th child was the best child. And all the subsequent children are going to have worse scores. So it searches them in parallel, okay, with the silk 4, okay? So the idea here is, well, if I think the value is going to be worse than the one I've got, why do I need their exact value? Why can't I just, check to see if it's less than alpha, okay, which is what's going on here, okay? So that's what it does. And then when it comes back, it says, oh, I get a value B, okay? And if it's bigger than my best score so far, I'll update B. Okay, now in fact, there's a race condition here, okay, but it's easy to resolve this race, okay? You can do it with atomics. There are other tricks that let you do it. You can do it with a compare and swap type thing, whatever. Okay, so you update B though. And then, so I haven't shown the atomicity here. That's something you're gonna have to do for yourself, okay? So if it happens to be better than beta, that's better than our best expectations. We didn't expect that we're going to get a cutoff because, we searched the first child and didn't get a cutoff. But we might get a cutoff. If so, we then are going to want to return S, but first we abort all computation we've started and we don't start any new ones. Okay, and implementing that, I'll talk about that briefly. However, if that doesn't happen, then either S is bigger than alpha, it's one of those blue nodes, or it's one of the red nodes. Okay, and if it happens to be one that's bigger than alpha, then what we're going to do is if it's smaller than alpha, it's like, okay, we confirmed it wasn't bigger, and it's not going to be the best move. But it's bigger than alpha, then we need to value it. Okay, and so now what we do is we wait for all the previous iterations to complete. Okay, all the ones from 0 up to I-1. Okay. And then we do, and this is where it's a little bit complicated to implement, okay? And this is where we're going to give you something that's a little bit easier. Then you go ahead and you do a full width window search, okay, of the node. So you search it a second time. Now, the second time is going to be a lot more expensive than the first time. Okay, the first time, even though it may have caused you to search again, really didn't take up that much effort because it was aggressively pruning. Now we actually do it. And now we repeat the stuff that we had from before, just like if it's bigger than beta, we abort and return all the others. If it's bigger than alpha, we update alpha. And if it's bigger than the best score so far, we make it be the one. And then we mark the completion of the ith iteration so that, in this step, others can check that we have done. And when we're done, we return our best score. Okay, so that's basically an overview of it. Okay, I'm going to run through an example. I'm not sure how much, whether I've actually, I think I might be able to slam through this, but you can do this yourself because you'll have the slides, okay? So I don't expect you to understand everything in real time, but if you try, but you will if you try to parallelize your bot, okay? By the way, hold off on parallelization until there's other things, okay? You may want to study it, you may want to plan for it, but parallelizing is not the first thing you want to be doing. There's so much low-hanging fruit in the code we gave you for performance, okay? Okay, so here's an example. In this example, we've already marched down the left side and we have found the value of S equals 3. And we're up here and Lavender wants to minimize. So it tests Lavender's other two children in parallel for whether S is greater than or equal to 3. So very similar to what we did. But now, instead of just really evaluating, we're actually just going to test whether they're greater than or equal to 3 using a 0 window search. That's what's different between this and just the simple young siblings weight algorithm. Okay, that's a 0 window search. Okay, so we only have to find if they're bigger than 3. Okay, so in this case, we can see that they are by just examining the first leaf in each of the two subtrees. Okay, and we've got good pruning because we don't have to worry about anything except whether it would be greater than or less than 3, unlike if we were doing a full window search. Okay, so we know then the value of Lavender at that node is equal to 3. because lavender takes the minimum of 3 and 2 things that are greater than 3. Okay. And now we can propagate that up to the tangerine root. And now we have, which is maximizing, we know the root's value must be at least 3. And now we have done the first child, okay, which is what we're supposed to do. Okay, value the first child. And so now we go and do a recursive zero window search of the other 2 children, okay, with a constraint that it be at most 3. Okay. So, so if in both of the subtrees we immediately get beta cutoffs as we go down the first subtree here and the first subtree here, we get beta cutoffs greater than 3. That's good. Okay, as the values are bigger, and we're doing so. We got good pruning because we are doing a zero window search. But now we've visited the first one, valued the first one, but now we are recursively doing zero window searches for s less than or equal to 3 here. And in the middle subtrees, these 2 here, okay, the tests fail. Okay, we don't get that it's less than or equal to 3 because after all, the maximum here is going to be 7 and 5, and this is going to take the minimum. Okay, so we're not going to get all the information we want. Okay, in the right subtree, okay, we have to examine all the leaves, but the test succeeds. Okay. So where are we here? Okay, so in the right subtree, the test succeeded, and we know that the value is at most 3. Okay, in the middle subtree, however, we've discovered that the test failed. Okay, and the value, okay, is greater than 3. Okay. So in this case, we have to wait for any preceding children to finish. Well, there's only one preceding child, and that's the one over here, which is already done. And then we recursively evaluate this subtree, okay, the whole subtree. We go search again, okay, with a full window search. And as I say, that may sound like it's expensive, but it turns out not to be a big issue. Okay, the recursive full window evaluation is still likely to take much more time, and the zero window search was a good, good test. We were speculating. And one of the things about Jamboree search is it speculates only on the zero window search. And since those tend to be less expensive than the full window searches, hey, we're making a bet that isn't too big. It's not too expensive. Okay. So now we have to recursively evaluate this, and we're doing a full window evaluation of this tree at this point. Okay, so we first search the first subtree, getting a value of 6, which we propagate to the root to conclude that S lies between 3 and 6. Okay, and now we do a recursive zero window search, okay, to find the values that are at least 6. Okay. And that lets us, we very quickly discover that, this value has failed, okay? And so the preceding, we have to wait for the preceding guys to be done. So we wait for this one to be done, okay? And now the middle one is done and its test succeeded. Okay, that's good. So now we have to do a recursive, since this one failed, we have to do a recursive full window search on this last subtree. Okay, so here we go and we do this one. Okay, so when we're wasting work, we're wasting it on something that was relatively cheap. Okay. Okay, and so then it computes the value 5. Okay, that gets propagated, the 5 gets propagated up to be that guy there. Okay, and then that gets, we now are able to take a maximum, okay, and we have the value 5 for the root. Okay, and so that's the example. So here's the pseudocode again. You'll probably want to study it on your own. And as I mentioned, it's got some races, which you'll need to resolve using locks, atomics, or other synchronization mechanisms. Okay, but it's actually not that big, but it does take a little getting your head around. Now in this, I mentioned abort, and I really didn't tell you how to do that, but it's very similar to the speculative computing code we saw before with found, okay? If we basically put in the search node structure an abort flag, okay, in every node, okay? And if a returning child was going to cause a beta cutoff, it sets its parent abort flag, okay? And during the search, each node, rather than trying to push values to other nodes, the nodes pull up the search tree to see whether any ancestor nodes are signaling an abort. And if it does, then it quits the search right there. It doesn't finish doing the search, okay? And so there's a little bit of tuning to do here. So you want to poll often enough to avoid wasting work, but not so often that the polling itself wastes work, okay? And there are a variety of ways I'm sure you can come up with to make that happen, okay? And then finally, after the last child returns, the parent can return, okay? So the Lyser-Chess code base is already structured to support a simple parallelization of scout search. Okay, so in the scout search routine, if you look in there, you'll find a place where it's going, it has got this move index and it's going, and this is basically going through the list of nodes, okay? And then it's getting the next move and so forth. And the way you parallelize it is very simple. You turn that 4 into a silk 4. Okay, pretty simple, but nothing so simple. There are some complications, okay? So this search is not quite the same as Jamboree search, but it should get you going, okay? And there are some, it turns out there's some slightly simpler options, and you'll see it's actually, I think, a better way of doing it, okay, that Tim Kaler actually pioneered. Okay. Now you have to worry about not just the races in this search code, but also the races in the actual code. And what you'll find is that there are 3 major places where you have races in what are called the best move history table, the killer table, and the transposition table. And so you're going to want to consider how you might address them. For example, you could synchronize, locking or using atomics. You can make worker local copies. You can just risk it. You can say, okay, I know there's a race, but I bet that it doesn't make any difference in my execution, okay? That's not worth trying to fix the race. I'm just going to guess that I'm going to get lucky as I run. Or perhaps that it doesn't affect correctness. It only affects performance. Or that it affects correctness, but the odds are so small, I'm not going to worry about it. There are a lot of things you can do. And then there are actually even other things you can do here. Okay, so that's basically a tour de force on Jamboree search and parallel search, okay? And to wrap things up, let me just review a few of the concepts from computer chess that you may find valuable. Some of these should be a review now that you've been on project 4 for a little while, but it may still be worth refreshing your memory. And I'd be happy after class to take any questions about any of these and give you all my best advice. I'm not going to hold back. So in the opening book, the idea is this is classic pre-computation right out of Bentley, okay? Pre-compute the best moves at the beginning of the game, okay? You know the starting position of all the pieces, figure out your first best move or first best moves. Most chess programs keep a bunch of opening moves and pick randomly among them. If you do decide to keep an extensive book, you should know it's cheaper to store 2 separate books for the 2 sides. Okay, if you're keeping both sides for dply, takes b to the d space. Where have we seen that? And also time to compute it. Whereas if you keep only one side for depth d, it's about square root of b to the d space, and only double that for both sides. So it's definitely a win to keep a book for each side. Iterative deepening, okay? Now, the way your code works is rather than searching a position to depth D right off the bat, you search it first to ply 1, then start over from the start and search it to ply 2, and then start over from the beginning and search it to ply 3 until you reach depth D, okay? Since the since the growth of work with ply is geometric, okay, the leaves account for most of the work. And all the searches up to depth D represent only a small increase in the work over going directly to D on the first search. Okay, so it's basically exponential. It doesn't cost you much to do it. But it turns out it's actually way better because the shallow searches can be used to populate the transposition table. And the transposition table move has the most likelihood of being the best move in a position. Okay, the one that you saw at depth D-1 is likely, that was best, is likely still the best one at depth D, even if the position wasn't searched to as deep a depth. And that makes pruning more effectively. In addition, some other advantages is that iterative deepening provides a good mechanism for time control because you can estimate based on the shallower ply whether you have time to complete another ply. Okay, so we've actually put a stub in the code base to make it easier for you to add an opening book if you choose that. And oh, that was a comment I was supposed to. Sorry, that is on the wrong slide. Sorry. Okay, we did put a stub to make it easier for you to do that. Okay. Endgame database. You can also keep an table of endgame positions, such as king versus king or king and pawn versus king. Okay, if there are a few enough pieces on the board, the idea is pre-compute the outcomes and store them in a database. Okay, in general, you have to worry about how big is that database, but you can be clever by compressing it and taking advantage of symmetries and so forth. Let me just say, it doesn't suffice generally to just store a win, loss, or draw for every position. If you only know that you have a win, but you don't know what move takes you closer to a one position, you can end up getting a draw because your bot will just cycle, okay, around winning positions, but never finding its way to the actual one position. Okay, and then the 50 move rule comes into effect and you get a draw. Okay. So most chess programs keep the distance to mate so they can always move towards the mate. Okay, so they know how far it is and they can always value a position that's closer to the mate higher. Okay, quiescent search. Okay, so you don't want to evaluate a position using a static evaluation function if the position isn't quiet. What do I mean by quiet? Well, let's take chess. Okay, suppose in chess, okay, you play queen takes queen, and that's the end of your search. At the very end of your search, white takes black's queen. Okay, so black may well be able to recapture. Say maybe his queen's protected by a pawn and he just plays pawn takes queen. But for the moment, it looks like you're up a whole queen. So quiescent search quiets the position before calling the static evaluation function. You don't want to call it and discover it. And typically what that means is only allowing captures or checks, or other important moves of that nature. And usually in quiescence, either side has the option of doing nothing, standing pat. Okay, so that's a way of quieting it. Make sure that when you evaluate it, your material is going to be properly considered. Okay, null move pruning. Okay, for many years, people worked on trying to figure out the best moves and search deeper in those areas of the search tree. And that never worked very well. Okay, there are a couple places where it helps, but it really is not that great a strategy. Okay, it turns out a better strategy is to find ways to reject bad moves, because most of the moves considered by a computer are not just bad, they're amazingly awful. Okay, and if you take a look at some of the positions, okay, that your bot is playing, you'll see it's like, oh my God, why is it bothering to look at this move? It's junk, okay? So the idea of null move pruning is to reject some of these truly awful positions, okay, with a shallower search, okay? And if you can reject some of these truly awful positions, you automatically are causing your program to spend more time on the good moves, okay? So the idea here is, suppose that my position is so good and yours so awful that even if I do nothing, I can still beat you handily, okay? So the idea is that without making a move, I can still beat you according to a shallower search. I'm not going to bother to explore that branch of the search any deeper, okay? So that's the idea of null move, and almost every chess program has it, okay? but you want to watch out for zugzwang. This is the situation where your position is safe, but if you do anything, you're finished. Okay, and that happens in chess. I'm not sure about in Lyser chess whether we have a zugzwang situation. Okay, another search heuristic is the killer move table. Okay, the same good moves tend to show up the same depth of search. So for example, suppose I'm threatening to take your queen with my rook. So you try moving a pawn. And my response, I'll take your queen with my rook. So you try moving your king. I take your queen with my rook. For most of your moves, I'm going to take your queen with my rook. That's a killer move, okay? And we want to order them near the front of the move ordering. Okay, so that's one thing. Another search heuristic is extensions. Okay, this is a case where you're looking to go a little bit deeper in an area you think is important. Okay, and typically chess programs do it when the king is in check on certain captures, or if the move is so-called singular, there's only one move in that position. Okay, and then you extend, you say, okay, well, I'm going to search recursorily, but I'm not going to decrement D. Okay, I'm going to leave D the same. Okay, now Zobrist hashing is really important to understand because you're going to want to mess with this especially if you change the representation. It's a scheme for incremental hashing. Suppose that you compute a hash of chess positions as you encounter them. So that hash function could be onerous to compute if there are a lot of pieces on the board because you got to have a big board and you got to, hash all of it. So Zobrist's idea was to compute the hash incrementally from the previous board position. And the way he does that is for every piece and every square, you generate, let's say, a 64-bit random integer. Okay. And now to compute the hash of a given board position, you go through all the pieces, find out the random word corresponding to the piece and square that it's on. Okay, so the piece and square determine a random number, and you XOR that value into the hash. And you do that for all the pieces. Okay, and that's the hash function for the board. Now to remove a piece from a square, you just have to XOR the random word corresponding to that piece and square into the hash. And poof, because of the self-inverse of XOR, the hash of the board position, it has been removed. It's the board position without that piece. And then if you want to place it on another square, you just XOR the random word corresponding to that piece and the new square into the hash. Okay, we've implemented Zobrist hashing for you, but there are many other opportunities, both in the hashing and to incrementally update state in your bot rather than recomputing from scratch. Okay, so you can definitely use this elsewhere in the code. Okay, I'm almost done here. The Zobrist, the transposition table is essential. Okay, it's actually, the search tree is actually a DAG. If you don't realize that, you don't want to be searching a node again. Okay, and not only can it remember the value you've got, it can remember the move and so forth. Okay, so there's several parameters that are kept there. Okay, transposition table move, iterative deepening. Okay, a good capture move, killers, losing moves, best moves. Okay, one of the things that is kept in there is the quality, and the quality is the depth that you've searched. Because generally, if you have a choice of which of two items to keep in a table, you tend to keep the one that represent more work. Okay, which one was backed up by more search. Okay. So typical move ordering, this is the order that they usually go through them. You can see transposition table is usually the first one. That may not be best for Lyser chess, but this is the order we've used them. Okay, there's another heuristic called late move reductions. The idea is, suppose you have a good move ordering, then a beta cutoff either occurs right away or not at all, or certainly within the first few moves. So the idea is search the first few moves normally, and then for the later moves, reduce the search depth, okay, saving work, okay, because you just don't think those are likely to be very good. Okay, futility pruning. Okay, the idea here is that if you only have one ply left to search, you can discard moves that cannot possibly raise alpha, okay, if you're far enough away from alpha. So after the static evaluation, you add a futility margin to the score of the current position. And if it doesn't exceed alpha, you say, I'm not going to even bother static evaluating it at the leaves. Okay. The board representation, this is something you want to eventually do, but maybe not right away. Okay. There are two basic ways you can keep a board. One is what's called a bit board, okay, where you use a 64-bit word, for example, to represent all the locations where pawns are on the 64 squares of the board. And then you can use word level parallelism to do tricks to, for example, do move generation in parallel using those bit tricks. Another strategy is what's called a piece list. You keep, instead of keeping the board, you keep just a list of the active pieces together with what squares they're on. And one of the nice things about this is that the list keeps getting shorter and shorter, so move generation keeps going faster. And then there are hybrids of these approaches. Okay, there's a lot more good stuff on the chess programming wiki. Okay, I encourage you to go take a look at it and browse some of the things that are there. You may get some good ideas. You can also get some background on what you're doing. And we're almost done in the class. Good luck on the quiz on Thursday, and happy Thanksgiving. And I'll hang around for if people want to talk or ask questions. See you later.